Magnetism can absolutely be described through molecular orbital theory. And if you remember from atomic orbital theory, if you had 1s2, 2s1, the 2s1 had a single box with an odd electron, so that was paramagnetic. Well, in a molecular orbital diagram, you just look and see, do you have any unpaired electrons? And you absolutely do. In O2, two individual electrons right there. O2 is absolutely paramagnetic. You've got unpaired electrons. They're in pi star antibonding orbitals, but that's it. Now remember, this is cool because O2's molecular orbital diagram shows that O2 is paramagnetic. If you're to draw the Lewis structure for O2 looks like that. There's no odd electrons running around on that thing. So MO is much cooler for oxygen's diagram than the Lewis structure is, which is kind of a neat thing. Dinitrogen is an NBC diagram. It's a 2-1-2-1. So you can see that here now the pi's are lower than the sigmas, but the pi star and the sigma star are the same. That's where the 2-1-2-1 comes from. Now, nitrogen, the atom, is 1s2, 2s2, 2p3. The 2p3 means we would draw 3 electrons on the left, 3 electrons on the right, and they'll combine 6 electrons in the middle, so the pi 2p is filled as well as the sigma 2p. But notice that every up electron has a down electron. There are no unpaired electrons, so N2 is diamagnetic. The Lewis structure for N2 is very, very close to the molecular orbital theory structure. N2's Lewis structure would look like that. It has a triple bond order of 3, just like molecular orbital diagram shows bond order of 3. N2's Lewis structure shows it to be diamagnetic, and so does the molecular orbital diagram. N2 would go right on through the magnet with no problem. Is N2 plus paramagnetic or diamagnetic? This is a cool kind of part about molecular orbital theory as well. It's easy to find if the ions of neutral atoms are paramagnetic or diamagnetic. Now, N2 plus means you've lost 1 electron. So if you look at N2, the diagram there on the right, N2 plus means that it's going to lose one of the electrons, and it's always the highest occupied molecular orbital electrons that come out first. So for N2 plus, we would take away one of those bonding sigma electrons. Then there would be just 1 electron left over. N2 plus is going to be paramagnetic. N2 minus, 1 extra electron, would also be paramagnetic because we'd have to add that extra electron to the lowest unoccupied molecular orbital, the pi star 2p. Pretty cool. It's easy to tell with molecular orbital diagrams, a lot of information on the ions of molecules if you have the default molecular orbital diagram listed. We'll look at that more in the problem set as well. Instead of drawing out the complicated 1-2-2-1s and 2-1-2-1 kind of diagrams, you can use a shorthand notation to represent your molecular orbital diagrams. These are really handy. They're a lot easier to draw in Microsoft Word or Google Docs than the full diagrams with pictures and stuff like that. Molecular orbital notation, a lot of times what they'll have is they'll have a core or core electrons, and that shows the orbitals which basically aren't interacting. If you have just as many bonding as anti-bonding orbitals, then you could just write core for those. Also with molecular orbital notation, you always want to go in increasing energy. So lowest energy on the left and highest energy on the right. That would be like going from the bottom to the top on the other diagrams. This is the molecular orbital diagram for N2 on the left, and it's pretty cool looking. In terms of a molecular orbital shorthand notation, all right, this down here would be how you'd write it. In this case, core, or core electrons in brackets, that's equivalent to the noble gas notation. So like lithium is a helium in brackets 2s1. Core, or core electrons in brackets, means that there's sigma 1s and sigma star 1s electrons, which are filled up. So for this shorthand notation, you would write core, and then notice the notation. Sigma 2s is in parentheses with a superscript 2. So this is the molecular orbital, the sigma 2s, parentheses, and then superscript represents the number of electrons. So sigma 2s2, sigma star 2s would be the next one, 2, pi 2p4. You can combine them both. You don't have to separate them. Pi 2p with 4 electrons, sigma 2p2. Once you get used to the notation, it is a lot easier to write than the diagrams on the left. I want you to draw, at least at first, some diagrams like the one on the left because it kind of shows where all this stuff comes together. But when you're used to it, the shorthand notation is definitely the way to go. So the question is, what's the bond order of N2 plus? All right, and there's 5 different possibilities there. Now, in the lower corner there, it shows the shorthand notation for the N2 molecule. And it said core, and then sigma 2s2, sigma star 2s2, etc., etc. When you're figuring out bond order, remember if the bonding and the anti-bonding are equal, they really don't participate in the bond order. So we can absolutely ignore the sigma 2s2 and the sigma star 2s2 electrons. They're not really part of the bonding. And we also saw earlier that N2 has a bond order of 3. That came from 1/2 parentheses, bonding minus anti-bonding parentheses, or 1/2 6 minus 0. And the 6 comes from the 4 of the pi 2p and the 2 of the sigma 2p. So 1/2 parentheses 6 minus 0 is where the bond order of 3 came from for neutral N2. Now N2 plus, we've taken away one of the bonding electrons. We're going to take away the sigma 2p, and so it'll only have sigma 2p1 after that. So bond order of N2 plus would be 1/2 parentheses 5 minus 0. We don't have 6 because we took away one of the sigma 2p's. 1/2 parentheses 5 minus 0, bond order 2.5, 2.5. Now you can easily represent partial bonds, like half bonds, in molecular orbital theory. In a Lewis structure, it's difficult to try and draw half bonds. Like we talked about how when an item resonates, sometimes you can have like fractional bonds. In molecular orbital theory, it's easy to talk about 2.5 bonds or 1.5 bonds because it's all about the raw electrons, all right? This is another advantage of MO theory. It's a lot better at talking about these partial bonds than any of the other systems we've looked at so far. You can also determine the number of sigma and pi bonds in a molecule using molecular orbital theory. When you're talking about sigma and pi bonds, you must focus on the sigma orbitals versus the pi orbitals, and you don't mix them together, all right? And then also along the way, just like we saw in chapter 7, number of sigma bonds plus number of pi bonds equals the bond order. So let's go back to N2 real fast. The Lewis structure for N2 looks like this. It's a triple bond, which means bond order of 3. And as we saw already now, the first line you draw is a sigma, so there would be 1 sigma, and the other lines you draw would be pi. So the triple bond order of 3, has 1 sigma plus 2 pi. And that's what we're going to do in the equivalent version here with molecular orbital diagrams. To figure out the number of sigma bonds, we're only going to look at the sigma orbitals. To figure out the pi bonds, we're only going to look at the pi bonds, pi orbitals. And finally, sigma plus pi will equal the overall bond order, which is a nice way to check yourself. So for N2, all right, here's the shorthand notation. Sigma 2s2, sigma star 2s2, pi 2p4, sigma 2p2. Notice here that in this picture, all of the sigma electrons are that kind of green color, and the pi electrons are the kind of orange color. So you can see there's 4 bonding pi's, and there's a total of 6 sigma electrons, but 2 of the sigma electrons are anti-bonding and the other ones are bonding. So if you want to figure out number of sigma bonds, 1/2 parentheses bonding minus antibonding, but just the sigma, all right? And in this molecule, these are bonding sigmas, these are bonding sigmas, so there's 4 bonding sigmas. We'll subtract the 2 anti-bonding sigmas, 1/2 4 minus 2, 1 sigma bond. We're going to do the same kind of thing for pi bonds. 1/2 parentheses bonding pi minus anti-bonding pi. There are no anti-bonding pi's. Those would be the ones up there, and those are empty for this diagram. So 1/2 parentheses 4 minus 0, bonding minus anti-bonding, 2 pi bonds. And the overall bond order, 1/2 parentheses bonding minus antibonding, well, this is the antibonding, and all the other ones here are the bonding. So 1/2 parentheses 8 minus 2 is 3. That would be the bond order, and that's good because that also equals the number of sigma plus the number of pi's. So a bunch of things here. First of all, bond order still equals 1/2 parentheses bonding minus antibonding. That'll give you a number. And sigma bonds, 1/2 bonding sigma minus antibonding sigma will give you the sigma bonds. Pi bonds, 1/2 bonding pi minus antibonding pi will give you the pi bonds. And if you've done it right, sigma plus pi will equal the overall bond order. That's a nice way to check yourself, all right? Finally, the N2 molecular orbital diagram is really, really close to the Lewis structure N2, which I kind of cheesy wrote up there. You're still going to have a bond order of 3, 1 sigma, and 1 pi, all right? If you're curious about where the lone pairs come from, the lone pairs come from these electrons right there. One of them is on the left nitrogen, one of them's on the right. Again, there's no molecular orbital diagram, so those electrons are being separate on each individual nitrogen. Oh, it's all coming together, and everything's diamagnetic. So N2 is a good success story for MO versus Lewis structure / valence bond theory. This picture here shows the MO diagrams for the neutral diatomics between B2 and Ne2. And there's a left and the right. On the left-hand side, we're seeing the 2, 1, 2, 1 diagrams where the pi's are first and then the sigma, then pi star and sigma star. On the right side, we're seeing the 1, 2, 2, 1 diagrams where the sigma now is first before the pi, then pi star and sigma star. And you can see how the things change. Bond order gets up to a high of 3 and then goes down to 0. Notice there the energy, bond enthalpy. That's essentially a measure of the energy. Remember in the last chapter we saw as bond order goes up, the bond energy goes up. We definitely see that bond order 3 has the most energy relative to 2s and 1s. Notice the 2 from C2 is different than the 2 from O2. That's because of the different electronic configurations. We also saw that as bond order goes up, the bond length goes down in a relative context. So you can see that as bond order is going up, the bond lengths they're represented in angstroms, that A with the circle on the top. Bond lengths are going down to nitrogen, and then they start going up and you go to the other side. And finally, you can also see the magnetism, all right? B2 and O2, of course, each have unpaired electrons there, so they're going to be paramagnetic while the others are generally diamagnetic. The reason they try and rationalize why there's the 2-1-2-1 versus 1-2-2-1 diagrams is because of the sp mixing and or electron repulsion. I don't really buy either one of them, so I think this is an area where scientists still have to figure some stuff out. But anyway, if you're curious why there's the NBC versus phone or the 2-1-2-1 versus 1-2-2-1, those are the reasons they give. I'm not totally in love with either one of them, though. Making the ions is actually pretty simple. We did some cheesy examples earlier. Let's formalize it right now. If you're making a cation, a positive charged version of your molecule, you're going to take an electron away from what's called the highest occupied molecular orbital. So O2 neutral had pi star 2p2. That there was 2 electrons in pi star 2p. But this diagram diagram is for O2 plus 1. So they took an electron away from an anti-bonding pi star 2p. Once you make the new ion, which by the way you can see is easy, you just add or subtract electrons, you need to recheck your bond orders, paramagnetism, diamagnetism. Another thing is that since we took away a pi star, an anti-bonding electron, we would expect the bond order to go up because we're taking away an anti-bonding electron. If you took away a bonding electron, we would expect the bond order to go down. We're destabilizing the molecule. But it's pretty easy, which again is an advantage for having an MO diagram. If you wanted to make O2 minus, you'd start with neutral O2, and the picture right there is of neutral O2. It's got the pi star 2p. And the question is here, where would you place the extra electron? Well, the extra electron will go in what's called the lowest unoccupied molecular orbital, the LUMO. The LUMO here would be a pi star 2p. That's the first place. You could pair up one of the electrons, either left or right, it doesn't matter. We are adding though an electron which is going in an anti-bonding orbital. So we would not expect the O2 minus 1 ion to be as stable. Adding anti-bonding electrons makes the molecule less stable. If you add bonding electrons, or if you take away anti-bonding electrons, you'll make the molecule more stable. So it's kind of cool how everything works out.
When light strikes an object, part of the light is reflected. In the eye, electrons in rhodopsin move from a pi bonding orbital to a pi anti-bonding orbital. One of the molecule's double bonds turns into a single bond, allowing rotation. The double bond then reforms, and the molecule locks into a new shape. The change in shape triggers a nerve impulse, and we perceive light.
This is a really cool use of molecular orbital theory, and it helps us to understand the process of seeing red. When your eye sees red, the light comes in, and it's the perfect, apparently, wavelength and energy to make one of the pi bonds in rhodopsin, this chemical, break apart. And what that means is the pi orbital, which initially has 2 electrons, one of the electrons gets enough energy to jump up to an anti-bonding pi orbital. And if you have just as many bonding pi as anti-bonding pi, it breaks that double bond. And by breaking the double bond, the molecule rotates into this meta-rhodopsin, which is kind of a cool name. And that transition allows a nerve impulse to go in our brains and say, hey, that's the color red. Pretty cool. After a while, the meta-rhodopsin relaxes back to rhodopsin, so it can absorb more light. You see more red and stuff like that. But anyway, this is a cool kind of thing. Rhodopsin is a really interesting compound. If this is something you're interested in, this would make a great class presentation molecule or compound. Rhodopsin, and the chemistry behind seeing is really neat. This is all photochemistry, using light to enact chemical change. Pretty cool stuff.
As a lithium crystal forms, the electrons and orbitals of individual atoms interact to form molecular orbitals. As more and more atoms join the crystal, the orbitals become so numerous that there are too many to account for with standard box notation. Instead, we describe a band of molecular orbitals which is spread or delocalized over all the atoms of the metal.
The third type of bonding is called metallic bonding, and we've seen a lot of examples with ionic bonding, positives and negatives. We've seen a lot of bonding examples with covalent bonding, which is nonmetals and nonmetals. But in metallic bonding, you have pure metals or combinations of metals, and when they mix, instead of having like one lithium atom, you'll have a whole bunch of lithium atoms, and they're all at the same energy. So those energies essentially mix together, and you end up with a whole bunch of occupied bonding molecular orbitals and a whole bunch of unoccupied, usually anti-bonding molecular orbitals. And if you add a 10 to the 23rd of these, they create what's called band theory, which is basically a separation between the bonding and the anti-bonding orbitals. This creates essentially what they call a sea of electrons, which flows over the metal. And these sea of electrons are why like metals conduct conduct electricity so well. Electron goes in one side and out the other because it's just a big sea of electrons. Very, very cool stuff. This is only possible, of course, if the molecular orbital energies are very close to each other. So alloys are generally metals that are similar molecular orbital wise to each other, but you do get excellent overlap. Metals will kind of bend a lot of times because the sea of electrons just flows with it. However, it's usually harder than to boil metals, because in boiling you break the band apart and stuff, makes it really tough. So band theory is pretty cool, and this also gives us a chance to talk about metallic bonding a little bit.